Today we are going to learn about handling memory constraints and sliding window attention. We will explore strategies to optimize memory usage in large language models, focusing on enhancing performance while managing resource limitations efficiently.
Welcome to our exploration of handling memory constraints and sliding window attention. In today's digital age, efficient memory management is crucial, especially when deploying large language models on resource-limited devices. Our focus will be on sliding window attention mechanisms, a technique increasingly used to manage memory effectively while maintaining performance. This video will guide you through a series of strategies, illustrating the challenges and offering solutions. We'll delve into techniques like sparse attention and memory checkpointing, and present a case study on optimizing memory for mobile applications. By the end, you will have a comprehensive understanding of how to manage memory constraints without compromising on computational efficiency. Before diving into specific strategies, it's essential to understand the memory limitations inherent in large language models, LLMs. These models, due to their size and complexity, demand significant memory resources. Several factors influence this memory usage, including the number of parameters, the depth of the model, and the type of attention mechanisms employed. The attention mechanism, particularly, plays a critical role as it requires storing a large amount of intermediate data during computation. As models grow in size and complexity, the memory requirements can exceed the capabilities of many devices, particularly those with limited resources like mobile devices or edge computing devices. This necessitates the development and application of resource optimization strategies to ensure that these powerful models can be deployed efficiently across various platforms. Sliding window attention is a technique used to reduce the memory footprint of language models. The fundamental idea is to limit the attention mechanism to a smaller, localized window of tokens instead of the entire sequence. This approach not only reduces memory usage but also speeds up computation by focusing attention on relevant parts of the input. The key benefit of this method is the significant reduction in the memory required for storing attention matrices. However, implementing sliding windows must be done carefully to ensure that the model's performance is not compromised. Effective application involves determining optimal window sizes and overlapping strategies to capture necessary contextual information. By balancing these factors, sliding window techniques can maintain high performance while significantly reducing memory demands. In optimizing memory usage, it's crucial to consider the trade-offs between memory consumption and computational cost. While reducing memory usage is beneficial, it can sometimes lead to increased computational demands. For instance, techniques like model pruning can decrease memory requirements but may increase the number of computational steps needed for inference. The challenge is to find a balance where memory reduction does not significantly impact the computational efficiency or the speed of the model. Various strategies can be employed to achieve this balance, including selective attention mechanisms, efficient data structures, and hardware-specific optimizations. Understanding these trade-offs allows developers to make informed decisions and tailor their approaches based on the specific requirements and constraints of their deployment environment.
Sparse attention is an effective strategy for reducing memory load in large language models. Unlike dense attention, which considers all possible interactions between tokens, sparse attention limits these interactions to a subset of relevant tokens. This reduction in interactions directly translates to a decrease in the memory required to store and compute the attention matrices. Sparse attention not only reduces memory usage but can also improve computational efficiency by focusing processing power on the most significant parts of the input. Implementing sparse attention involves techniques like locality-sensitive hashing or fixed patterns that dictate which tokens should interact. These methods enable large models to operate within the memory limits of constrained environments while maintaining performance.
Memory checkpointing is a powerful strategy to manage memory usage during the training and inference of large language models. The principle behind checkpointing is to store only essential data points at certain intervals, allowing non-critical information to be discarded and recalculated when needed. This approach significantly reduces the memory footprint during model execution. While this method may introduce additional computational overhead due to repeated calculations, the trade-off is often worth it for memory-constrained environments. Implementing checkpointing involves determining strategic points in the model where data can be safely discarded and later recomputed. Successful application requires a careful balance to ensure that memory savings do not detrimentally affect the model's performance or training time.
Deploying large language models on mobile devices presents unique challenges due to limited memory and computational resources. This case study explores the application of memory optimization strategies, focusing on sliding window and sparse attention techniques. By implementing these methods, developers can significantly reduce the memory demands of language models, enabling their deployment on mobile platforms without sacrificing performance. Real-world applications show that these optimizations can lead to improved model efficiency and user experience. For example, in mobile voice assistants, optimizing memory usage allows for quicker response times and a broader range of functionalities. This case study illustrates the potential of memory optimization strategies in overcoming resource constraints and opens up possibilities for deploying sophisticated AI models across a wider array of devices.
Benchmarking is a critical process in evaluating the effectiveness of memory optimization strategies. By assessing memory usage improvements, developers can quantify the impact of various techniques and make informed decisions about their implementation. Benchmarking involves measuring the memory consumption of different models and configurations, often using specialized tools and frameworks designed for this purpose. Comparative analysis of techniques like sliding window, sparse attention, and checkpointing provides valuable insights into their relative benefits and trade-offs. Recent studies highlight significant memory savings achieved through these methods, emphasizing the importance of continuous benchmarking and driving advancements in memory-efficient AI. By maintaining a rigorous benchmarking process, developers can ensure that their models remain competitive and efficient in resource-constrained environments.
As the field of AI continues to evolve, future trends in memory-efficient large language models, LLMs, are poised to bring significant advancements. Emerging techniques focus on further reducing memory usage while enhancing model performance. Innovations in both hardware and software are driving these developments, enabling models to scale more effectively and operate within the constraints of various devices. The integration of memory-efficient LLMs with edge computing environments is particularly promising, as it allows for real-time processing and decision-making closer to data sources. Predictions for the future include the development of more adaptive and dynamic memory management strategies, leveraging advancements in AI to create models that can intelligently allocate resources based on context and demand. These trends underscore the importance of ongoing research and innovation in the quest for more efficient and scalable AI solutions.
In conclusion, handling memory constraints and sliding window attention is a vital aspect of deploying large language models efficiently, particularly on devices with limited resources. Throughout this video, we've examined a variety of strategies, including sliding window techniques, sparse attention, and memory checkpointing, each offering unique benefits and trade-offs. Efficient resource management not only enhances the deployment of models but also ensures that they can scale and operate effectively across different environments. As we look to the future, continuous improvement and innovation in memory optimization will remain crucial in advancing the capabilities of AI. We hope this video has provided you with valuable insights and practical skills to apply in your own work. Thank you for joining us on this educational journey.